everyone, welcome back to the channel. Today we will explore some vital concepts in C# that can help you write more efficient applications. We will be discussing processes, threads, concurrency, and asynchronous programming. These topics might seem daunting initially, but don't worry, we will break them down step by step. Without further ado, let's dive right in. Let's begin with the concept of a process. A process is essentially an instance of a program that is currently being executed. Think of it as a container that holds a program's code and its current activity. A process can be any application such as Visual Studio or a web browser. Each process has its own memory space, which ensures that one process does not interfere with another. Each process has a main thread. Additionally, each process has its own memory stack and heap, which are isolated from each other. Another important concept is program counter or PC, which keeps track of the number of executed code. The program counter is particularly useful during the context switching, a topic we will discuss in detail shortly. Each process may consist of one or more threads, each with its own memory space. However, each thread only has a stack. These threads are often referred to as worker threads. If a variable in a thread is a value type, it will be saved in the stack. Otherwise, its reference will be saved here and the value will be stored in the heap as we discussed earlier. In previous discussions, we talked about how GC managed the heap. When a program is completed, its allocated space is returned and GC takes care of memory management. The CPU is responsible for running these processes. Now you might ask, can we run multiple applications? But how does the CPU manage and schedule these applications? Let's take a look into that one. Now let's explore how the CPU schedules each process. There are various algorithms for this purpose, but in this video we will discuss the following: first come, first serve, shortest job first, and round robin. Let's discuss the first come, first serve algorithm. Consider a CPU with a single core and we have multiple processes. For example, in this case, process 1 needs 10 seconds to complete. Then process 2 requires 20 seconds to get complete. After that, process 3 requires an indefinite amount of time to complete. And finally, process 4 only needs 5 seconds to finish. Initially, process 1 is completed after 10 seconds, then process 2 is completed, followed by process 3, which requires an unlimited amount of time. As a result, CPU becomes stuck, leading to what is known as a starvation. This scenario is not fair because the CPU becomes unable to handle other processes while stuck on process 3. Let's discuss the shortest job first algorithm. Similar to the previous example, we have a single core CPU and 3 different processes. P1 takes 10 seconds, P2 takes 20 seconds, and P3 takes 40 seconds to complete. In this approach, the CPU will select the shortest job first, meaning it will select P1, then P2, and finally P3. Now consider that we have 2 new processes coming. The first process needs 10 seconds and the second one needs 20 seconds. So at first, the CPU will select the shortest one. After completing the shortest one and before selecting the second process, a new one will come that needs 5 seconds. The CPU will prioritize the first process over the second. After completing the first process, before the CPU can select the second one, another process that requires 50 seconds appears. The CPU then selects this new process and the cycle continues. Then a new process that needs 2 seconds arrives. This leads to a situation where the CPU never gets a chance to start working on the second process, which is not ideal and can be considered a form of starvation. Let's discuss the round-robin CPU scheduling algorithm. In this algorithm, each process is assigned a fixed time slot in a cyclical manner. For example, let's say we have 3 processes, P1, P2, and P3, and a single core CPU, like before. The processes are given their own time to complete, and we represent this using a time bar. In this algorithm, we have a fixed time slot. For example, we are going to consider 20 seconds as the time quantum. The CPU will spend 20 seconds processing process 1. Then it will move on to process 2 and spend 20 seconds on that one, and so on. The act of switching between processes is called a context switch. After spending 20 seconds on P2 CPU, the system will select P3, prompting another context switch. As a quick reminder, during a context switch, the CPU needs to remember the previous progress, so it stores the executed line number in the program counter, PC, as mentioned before. The CPU continues its work until one of these processes is completed. In this case, it's P3. Then the CPU continues its work until all of these processes are completed. In this method, there is no starvation, and this method is one of the most widely used methods in the CPU scheduling. Now let's have a deeper look into the round-robin algorithm. Consider that we have many processes from P1 to many other processes. In the first step, they will go to the ready status. In the ready, we have a queue and all these processes will get queued. As it's a queue, it is a first time, first serve quantum system. The CPU will begin running the first process. If the process is completed within the designated time period, it will be terminated. If not, it will be moved to the end of the queue and the CPU will select the next process. If a process is I/O bound and requires an I/O request, its status will be wait block. In this state, the process will wait until it receives a response from the I/O. Once it receives a response, it will move to the end of the queue. At times during this process, when it's waiting for I/O, the memory might become full. In this scenario, the process will enter the suspend wait status and release the allocated memory space. When it receives the result from the I/O, it will move to the suspend ready status, and finally, it will go to the end of the queue. This cycle repeats indefinitely until all processes are completed, and this is how concurrency works. Now let's examine the C# code to understand how synchronous and asynchronous processes work. There are 2 threads, the worker thread and the main thread. In each thread, we are outputting something, empty for the main thread and T1 for the worker thread. Let's revisit the process structure. A process includes code and memory, a main thread, and a worker thread. However, a worker thread is optional. Each worker thread has its memory. In the example code, the main thread will write empty 1000 times, and the worker thread will write T1. Based on the time quantum we discussed previously, there should be a context switch between these 2 threads. Therefore, we should observe a combination of MT and T1. Let me run the project As you can see here, initially empty was written. However, the output on your computer may differ based on your CPU's time quantum. The worker thread wrote T1, and this context switch continued until we end up with just T1. I was wondering what would happen if I used the join method. When I ran the application again, the first worker thread was completed, and then the main thread got blocked until the worker thread was completed. After that, the main thread started working. Let me draw the process again to explain what happened. As I mentioned before, we have a main thread writing empty and a worker thread that writes T1. In this scenario, the main thread waits for the worker thread to complete its task before it continues working. In synchronous programming, the main thread waits for the worker thread to complete before it continues working. This results in blocking threads. On the other hand, in asynchronous programming, there is context switch between threads, allowing the CPU to run a bit of each thread in each time quantum, which prevents any thread from getting blocked. To sum up, understanding processes, threads, concurrency, and asynchronous programming is crucial for developing efficient and responsive C# application. Processes are containers for your running programs. Threads are the unit of execution within this process. Concurrency ensures multitasks make progress simultaneously, and asynchronous programming helps keep your application responsive during long-running operations. Thank you for joining me today. I hope this video has clarified these important concepts for you. If you have any questions, please leave a comment below. Don't forget to like, subscribe, and hit the bell icon to stay updated with our latest content. Cheers and happy coding!